Hey everyone, and welcome to This Explainer. Today we're diving into something that is literally pulling science fiction into reality. If you've ever watched a movie and wondered just how close we are to having true, real-time holographic communication, the classic glowing 3D projection in the middle of the room, well, you're in exactly the right place. We are unpacking a genuinely fascinating piece of research from Google and the University of Washington. They've tackled a massive hurdle in rendering 3D video, which is this really stubborn issue known as the forgetful AI problem.
Okay, let's jump right into a visual puzzle to set the stage. Imagine I only show a computer the front-facing view of a subject, like the front of a pink hoodie. How on earth does the rendering system know to display a specific intricate gold leaf logo on the back of that hoodie when the person turns around? In a real-world broadcast, you usually only have a sparse, limited camera setup, so when the camera only captures the front, traditional AI systems literally forget what the back looks like the second it's out of view. So, what we're really talking about here is giving AI a human-like sense of object permanence. You know how a baby eventually learns that a toy hidden under a blanket still exists? It's exactly like that. An AI system needs that same object permanence to recall hidden visual details without constantly having a camera pointed directly at them. It has to be able to seamlessly hold on to information across both space and time. To put this into perspective, when we render dynamic 3D video, a pretty complex process known as novel view synthesis, we are constantly trying to generate camera angles that don't actually exist in the physical room. When a subject turns around and those physical cameras lose sight of their back, the AI is forced to rely entirely on its memory. It has to dig deep into its historical context, searching its own memory banks for what it saw seconds or even a full minute ago, just to flawlessly reconstruct something like a hidden logo.
Now you might be wondering, and it's a totally fair question, why don't we just force the system to constantly memorize every single frame of the live video stream? I mean, if memory is the issue, just throw more memory at it, right? Well, doing that introduces a massive computational bottleneck. Standard models actually require these heavy gradient-based memory updates on every single frame just to adapt to human motion.
Let's really break down the visual data here to see why that's a problem. Notice that spiking purple curve on the graph? That represents traditional, state-of-the-art models like temporal LVSM. They suffer from what computer scientists call quadratic complexity. Basically, as the video broadcast gets longer, the math gets exponentially heavier. The system tries to compute these dense, complex connections across every single past observation. And because of that, processing time skyrockets to nearly 460 milliseconds per frame. You cannot live stream with that kind of lag. It's impossible. So, the takeaway here is that this quadratic cost completely kills real-time streaming. You can't have a fluid, holographic conversation if the system crashes under the weight of its own memory every 30 seconds. But this is where our subject today, neural space-time memory, or NSTM for short, comes in and completely shatters that bottleneck. Instead of that spiking quadratic curve, NSTM maintains a flat, constant O of 1 complexity. Simply put, the processing speed stays exactly the same no matter how long the stream runs.
By flattening out that computational curve, NSTM is able to operate at a blistering 28.1 milliseconds per frame. And it sustains this ultra-fast, real-time speed on just a single H100 GPU. That massive 460 millisecond lag from the older models we just looked at, it's completely eliminated.
So, how did they actually pull this off? The researchers designed a really brilliant space-time memory structure. You can think of this architecture like a persistent 3D memory cube, a continuous vault of the subject. The AI internalizes the entire geometry of the scene into these things called fast waits, which totally bypasses the need to obsessively look back through every single past frame of the video. But the true genius, the real aha moment of this paper, is their decoupled approach. Instead of rigidly forcing the system to update its heavy memory on every single frame, they split the workload. The system updates its heavy memory very slowly, capturing the state at just 1 frame per second. But it queries that memory to synthesize the fast-paced video output at a buttery smooth 30 frames per second.
Now, if you're tracking with me, you might spot a potential flaw here. If your memory only updates once a second, but the human subject is moving at 30 frames a second, wouldn't you get a mismatch? Well, yes, you would, but NSTM bridges this natural gap using a clever cross-view attention mechanism. It explicitly looks at the live, fast-paced camera motion and dynamically fuses it together with the slow historical context stored in its memory vault.
Even with that fix, there's another hurdle. Over a minute-long broadcast, AI tends to slowly forget details or hallucinate weird visual artifacts, a well-known issue called catastrophic drift. To prevent this, the researchers introduced two crucial safeguards. First, an auxiliary loss rule that strictly forces the network to hold on to the scene geometry. And second, a memory caching strategy that basically locks down those active memory weights, protecting them from degrading over time.
Okay, let's really look at the visual evidence here, because when they put this to the test on complex human motion data sets, the results are just striking. Follow the progression from left to right. We start at time 0, where the cameras clearly see the subject's backs, but full 60 seconds later, the cameras only see their fronts. The middle sections show what the leading competitor models guess the back looks like compared to our NSTM model and the actual ground truth on the far right.
Let's isolate that pink hoodie example we talked about earlier. At time 0, the AI saw the gold leaf logo. 60 seconds pass, the person turns around. If you look at the breakdown here, only NSTM faithfully recalls and renders that exact logo from its persistent memory. The competing models lacked NVS, Token Mem, and LVSM. They completely fail. They essentially hallucinate a blank pink hoodie, entirely forgetting that the logo ever existed.
And this flawless recall holds up across all the tests. If we look at the other rows, whether it's accurately reconstructing the really intricate black crisscross straps on a dress, or rendering a large white emblem on a red hoodie, NSTM locks those details in. It's fascinating because stateless models, like LVSM, fail entirely because they literally don't have a memory mechanism built in. And the older stateful models, they suffer from that catastrophic drift we mentioned, where the details just slowly wash out into a blurry mess over that 60-second window.
And the visual proof is totally backed up by hard data. When evaluated on the absolute final frame of a 60-second sequence, which is basically the ultimate stress test for long-horizon memory, NSTM beats its closest competitor, lacked NVS, by nearly 3 decibels in signal-to-noise ratio. That is massive. It is absolute quantitative proof that this decoupled architecture genuinely solves the memory retention problem. So, by decoupling the slow, heavy process of memorization from the ultra-fast process of video synthesis, NSTM has essentially solved the forgetful AI problem, and it did it without sacrificing real-time speed. It's just a remarkably elegant solution to a huge bottleneck, and it leaves us with a really exciting question to ponder. If AI systems can now flawlessly remember and instantly render dynamic photorealistic humans from any angle over long broadcasts, how quickly are we going to see this completely reshape live sports, interactive gaming, and the actual reality of 3D holographic telepresence? Honestly, the future of how we connect digitally just got a whole lot clearer. Thanks so much for joining me for this explainer, and I will catch you on the next one.